Well, good afternoon, grade 11s, and welcome to a lesson on something we call relative motion. Okay, now I call them airplane and riverboat problems. Okay, and it's another example, like so far with two-dimensional motion, we've looked at how to add vectors like displacement vectors. All right, well, that's one thing you can do. Another thing you can do is you can work out, okay, what we call relative motion problems. And these relative motion problems are necessary part of training if you want to fly an airplane someday. Or, not really necessary, I guess, if you're captaining a boat, because they let anyone do that. But depending on the boat, okay. And for now, what I'm going to do is I'm going to show you an example of how you would navigate a boat across a river. Okay, so if you look at what you're seeing on your screen right now, you're seeing a boat that's about to cross a river. Now this river has current that is flowing towards the east. Okay, now the boat is pointing itself due north. And watch what happens when I click on run. See, the boat is pointing north, but it's actually traveling east of north because the current, let me pause it here, the current is actually forcing the boat to move eastward while it moves northward. Okay, now there's a little triangle there in the picture that is showing you the boat's velocity relative to the river. It's pointing straight up. Then there's the river's velocity relative to the earth, which is the current itself. So the river has current, flows, okay? And then the resultant velocity is the sum of those two velocities, right? The boat relative to the river. Okay, so the boat points north and has a certain velocity relative to the water, but the water itself is moving, carrying the boat downstream. Okay, and so, yeah, that's it. Now, let's say, I'm gonna reset this. Let's say I did not wanna go downstream. Let's say there's a dock straight across the river. How will I point my boat? Well, if I point with the current, then I'm never going to make it. I'm going to travel that way. And what if I want to get to the red dot up here at the top? Well, the boat traveling off in this direction does not help me at all. So obviously pointing along with the current doesn't help. But what if I point into the current? Okay, now if I point into the current, right about here, roughly, okay, pointing into the current, I'm directing myself west of north, or 47 degrees west of north. Now, if I run it now, will I make it to my destination? Now, this is going to look a little strange, okay? But if you take a look at the boat, he's trying to make it to the red dot. He's got to counter the current, and I'm just barely making it. He makes it there to his red dot destination. He traveled straight across. So in other words, sometimes the boat wishes to go straight across. You don't just point your boat across and see what happens. Usually you have a destination in mind. Now, by the way, the same is true of airplanes. Airplanes fly through the air, and the thing is the air doesn't have current, but it has wind. Okay, and wind does affect the direction of travel over the ground. And for airplanes, this is crucial because they fly like very large distances. So if you're not pointing the right way, you could be way off course. And planes only carry so much fuel. So if you're traveling from here to Yellowknife, let's say, in an airplane, and that pilot is off course, well, you're going to carry enough fuel to get you there. But if you miss the airport because you're a couple of degrees off course, and now you can't even see the airport when you get there because it's not close enough to see it. You could be hundreds of kilometers away from it, and you're running low on fuel. So this is a crucial skill. Sure, they have GPS and autopilot and stuff like that, but that technology can fail. And so the pilot needs to be able to do these calculations and work out how to control his airplane properly, or his or her airplane, right? All right, so now that you've seen this little animation here, let's go to OneNote. And let's take a look, okay, at how we do the calculations themselves. Okay, so relative velocity. I call these problems AKA airplane and riverboat problems. Because that's really what they are, airplane and riverboat problems. All right, let's take a look at these pictures here. Here we see this little triangle. Here the boat pointed straight across, but we see that it's actually going to travel this way, okay? And let me explain using this little vector diagram here what we're looking at. All right, so what the app here calls the boat's velocity relative to the river, so that's VBR, okay, the boat's velocity relative to the river. I call it VP. Let me use a different color. The rainbow one's a little weird there. I call it VP. Now, what I mean by that is this is the pilot's velocity. In other words, if you're the pilot of the boat, you're the captain of the boat, whatever you want to call them, what you're doing is you point the boat where you want. So in this case, you point the boat north. That is called your heading, how you point your boat. Now you also control the length of this vector, which is your speed control. There's a throttle on the boat. You can control the speed, and you can also control which way it's pointing. Now, this one here, the river's velocity relative to the earth, this vector, I call that velocity of the current. Okay, it's actually the current, right? So the current in the water is the velocity of the river or the water relative to the earth. Now, this last vector here, let me color the pilot one blue. So this blue one you control. You point your boat, you do what you have to do, right? Point your boat, you set your throttle, you control the length of this vector and the direction of this vector. The current I'm going to color red, okay? You have no control over this. This is nature controls this one. This is the current, or if you were an airplane, it's the wind, okay? And then finally, the rainbow vector, which is the sum of the other two, I'm going to color this with the rainbow. This vector here, okay, is called they say the boat's velocity relative to the earth. That's what they said down here. I'm going to call it the ground velocity. Let me make that a little more clear. The ground velocity. So it's the velocity of the boat relative to the ground. Okay, so the boat is going to move along that path. Now it's funny because it's not pointing that way, not the boat anyway. The boat is pointing just north. It just travels this way. Okay, so over the earth, that is. So it's traveling along this path. It's pointing this way, as you can see. But you see the current makes it travel along that path. And see, if you get that here, I want you to notice that right there where the red and blue vector meet, we call it tip to tail. The vectors are joined tip to tail, but notice that the current here is joined tip to tip with my ground velocity, okay? So you need to draw the vectors in the right place in the diagram. It's kind of crucial. And you cannot do these questions with component method. You've got to draw the picture, okay? The component method with these kind of questions is very difficult, to be honest, even when it's not a right angle triangle. So that's why I taught you sine and cosine law. And that's why we went over those. I mean, you learned it in grade 10. We went over it a little because you're going to need it for this. Okay, so here in this work, I'm going to give you some practice problems with this. With this one, you cannot use component method. You can try it if you want, but trust me when I say it's actually kind of complicated and you will get stuck if you try using the component method to solve these questions. A lot of them are right angle triangles, so you'd be happy about that. but there'll be some that aren't right angle triangles, and that takes practice, and that's it. Now here, I just wanted to point out in this example, notice how the pilot has changed his heading, okay? So look at this. Remember the pilot controls the blue vector. Okay, so let's go back to this one here. Now the blue vector is pointing into the current. So this is what the pilot is doing to the boat. He's pointing it this way. So he points the nose in that direction, right? So that's VP. That's what the pilot does, okay? The red vector, the current has not changed. Okay, the current in the Ottawa River does not change based on how you point your boat. It just is what it is. Okay, so that is still VC, the current. Okay, hasn't changed at all from the previous example. But now look at what happens. Now you're traveling straight across, and maybe that's what you wish to do, right? So I just want to point out that the rainbow vector here, the ground velocity, okay, this is what you wish to do, okay? So in other words, if I wish to go straight across, I have to point my boat along the blue line, along the blue vector, in order to travel straight across it. That's what I wish to do, okay? So you have to compensate for the current. So if I wish to go north, like I've got in this particular example, then I'll have to point west of north like this, so many degrees west of north. I'll have to point that way in order to do it, okay? And here, I guess the guy wishes, this is what he wishes to do, right? So if he wishes to go downstream like that, well, okay, when you point your boat due north, now you're gonna travel, you know, east of north because the current will carry you like that along the rainbow line, okay? But you point your boat north because what you wish to do is go along that ground velocity line or the rainbow line. All right, so now that you've seen, we've gotten our way around some of these vectors, let me summarize it for you underneath, okay? So I'm just gonna say note, a couple of notes here. So we'll go with our black vector, or black pen, sorry. I'm so used to saying vector, look what I did there. Okay, so notes. VP is the ship or the plane, okay, etc. It is your heading and throttle speed. For planes, sometimes we call it airspeed, okay? So you set the throttle. It's like pressing the gas pedal on a car, okay? You set the throttle to a certain speed and that's it. So the pilot, okay, the pilot controls both of those things, the heading and the throttle speed. That's VP. Now, VC, okay, or if you like, VW is the velocity of the wind, planes, or current for boats, okay? And then finally, VG is the velocity of the craft whether it's a plane or a boat, relative to the ground, okay? And this is what the pilot wishes to do. He wishes to, usually an airplane pilot wishes to fly between two airports on the ground. So he wishes to have a certain ground velocity, okay? All right, so now that we've summarized this, I'll just, another couple of notes. All vectors must have same units. So that's either meters per second or kilometers per hour. Okay. And yeah, I mean, that's basically it. So that is a summary of everything you need to know. Now let's do some examples because I know you appreciate that. So let's look at a couple of examples. We'll start with a right angle triangle. Okay, so let's keep it simple. Examples of how to do this. Number one, let's make this easy. Let's say the pilot points his boat that way, so north, and he points it north. Oh, actually, you know what? Let me be consistent. I'll use blue for that. So let's say the pilot points his boat north, and he's going 15 kilometers per hour north, like that. Okay, that's how he points his boat. Now, the current is going east. Let's make it 6 kilometers per hour. Now, my question for you is, what is the ground velocity? So the ground velocity will be the sum of those two vectors, tip to tail. Okay, so to answer the question, I'll need theta and I need my vector like that. What is my ground velocity? All right, so this is a right angle triangle because north and east here, this one is east, north and east are perpendicular. Everything's in kilometers per hour, so I'm just going to leave it. Since it's a right triangle, I can use Pythagorean theorem. So I'm going to write VG squared equals 15 squared plus 6 squared. Okay, so therefore VG is equal to, calculator seems to be missing. Okay, so let me do it for you. 15 squared plus 6 squared equals square root. I get 16.2. So 16, no, that's not right. Yeah, oh no, that is right. 16.2 kilometers per hour. But that's not good enough. I need theta also. So I'm going to write tan of theta equals 6 over 15. So now I'll find theta, 6 divided by 15. I go inverse tan of that, and I get 21.8 degrees. So theta equals 21.8 degrees, and that would be east of north. I can tell by looking at the picture that the rainbow line is east of the north line. So therefore, now I'll put my direction over here. My actual ground velocity is 16.2 kilometers per hour, 21.8 degrees east of north. Now we can only assume that this is what the pilot of the boat actually wishes to do. Okay. All right, well, that's pretty straightforward. Okay, now let me give you another problem. A plane wishes to fly. A plane wishes to fly south. Okay, but the wind. Let me here. Let me finish this. He wishes to fly south at, and let's make it 250 kilometers per hour. They're planes after all, they can go really fast. So that's what the pilot wishes to do, okay? The wind at altitude is, let's make it 50 kilometers per hour west, okay? The question is, what is the airspeed and heading? Okay, in other words, this here is VP. It's what the pilot has control over. He has control over these two things. But this south at 250, I'll highlight it in yellow, is what he wishes to do. Okay, it says right there, he wishes to do that. So that's the ground velocity. So this one here has to be the ground velocity. And finally, the wind is, here, I'll rainbow the wind. The wind is 50, that's obviously the wind, okay? So here we have our three vectors. Now, the trick of getting this correct is to construct your triangle correctly, okay? Like you have to construct it right. So I'm gonna put what they wish to do first. So he wishes to go south. So I'm gonna draw a south vector, and the south vector is 250. Okay, now this is tricky, this diagram, so pay careful attention to it, okay? So this is what he wishes to do, okay? But here's the trouble. The wind is blowing 50 kilometers per hour west. Now I'm gonna draw the wind using the red color for wind. I'm gonna draw it over here. That's 50 west. He wants to do 250. So this one's 250. Now, where do I put that red vector? Okay, do I put it here? A lot of students would put it there. Okay, do I put it here? Do I put it here or do I put it there? There's actually two correct answers and two incorrect answers. And I'm going to erase right now the incorrect answers. But before I do that, I want you to come back up here and I want you to notice something. Okay, so here in my little pictures, notice how the red vector, okay, I'm going to highlight it, the red vector here and the rainbow vector here are joined tip to tip. Okay, they're joined tip to tip. And the blue vector here, this blue vector and the red vector are joined tip to tail. So the tip is the business end of the arrow, right? It's the sharp end, the pointy end. The tail is the other end, where the feathers are on a real arrow, okay? So notice that the blue and red, what the pilot has control over is VP, and the current, they have to be tip to tail. And the rainbow vector, which is the ground velocity, has to be tip to tip with the current. Now, with that in mind, let's go back to our example. Which vector, the red one has to be tip to tip with the rainbow. Well, there's only one vector like that. It's not this one, okay? It's not this one. It's actually not this one either, although I'll honestly say that that does work, okay? You could do tail to tail method, but we're gonna do tip to tip. So here, those two, that's tip to tip. You must, when it's worded like they wish to do something, remember that what you wish to do is the ground velocity, okay? That's what you wish. Whereas this one here is the wind, okay? And they have to be tip to tip. Now we see what the pilot has to do. The pilot needs to go tip to tail with the wind. So he's gonna point his plane like that. And this is VP. This is the one we're looking for. And we're looking for that direction there. Now we know the wind. We know the wind is 50. So this side here is 50. Okay. And we know this is 90 degrees because west and south make a 90-degree angle with each other. So again, it's a right angle triangle. But this time we're looking for the hypotenuse of this one. So it's going to be VP, oh, let me go back to black. VP squared will equal 250 squared plus 50 squared. So we'll just take our calculator and I'll go 250 squared plus 50 squared equals 65,000, take the square root. I get 254.95. So he actually has to go 254.6 kilometers per hour. That's actually faster than what he wishes to do, but he has to go into the wind. So he has to increase his throttle in order to do that, okay? Now, let me erase this where I put the wind over here. Now we need to know the direction. So to get the direction, I'm going to go tan of theta is equal to 50 over 250. So I go 50 divided by 250. It's opposite over adjacent, right? And then I take the inverse tan. I get 11.3 degrees. So theta equals 11.3 degrees. And if you look at my line, it is east of south. East of south. So that is your heading. And that is your airspeed. So what does the pilot do? The pilot sets his throttle, which is the speed of the plane through the air, to this number here. And he sets his heading to 11.3 degrees east of south. And the wind will blow him back to the south line. So he's going to end up traveling along this beautiful looking rainbow line. Okay. So that's the rainbow line here. He's going to end up traveling along that line. See, so he has to point his plane that way, okay? Like, so now he has to go 11 degrees east of south in order to travel south because of the wind. So that crosswind has to be compensated for. Okay, and there you go. That's how you do a wishes to fly question. I can't leave you without doing at least one that's not a right angle triangle. So let's try another wishes to fly question. So we'll call this example number 3. So number 3, a pilot wishes to fly. Now watch how this is going to be worded slightly differently. East, okay. The airspeed throttle is set to 350 kilometers per hour. Okay. The wind is blowing at 70 kilometers per hour. So this is stormy weather, maybe 70 kilometers per hour. And I'm going to make this wind 30 degrees. South of west. Just making this up. South of west. Should I make it that hard? Yeah, I'll make it that hard. Okay, so there you go. Now the question is, what is the heading? What should the pilot, here, let me phrase it differently. How should the pilot adjust her heading? Okay, so how should she adjust her heading? What heading should she take? Now notice very carefully here, the pilot wishes to fly east. Now that is our rainbow vector. That is our ground velocity, what they wish to do. But the airspeed, I'll underline this in blue, the airspeed is the throttle. The pilot has control of that. Okay. Now what we're asking you for is the other part of that. What direction? This is also the pilot here for the heading. Now, of course, this one here is the wind, 70 kilometers per hour, 30 degrees south of west is the wind. So let's try this one, see what happens. So again, the way we started is the pilot wishes to fly east. Now, we actually don't know how long this vector is this time because it doesn't say what the resulting ground velocity is. So this is what the pilot wishes to do. Now, again, we have to go tip to tip with the wind. Okay, now, actually, let me give myself a little more room. Pardon me. I need room to write above it this time. Okay, so the wind is 30 degrees south of west. So what I have to do is I'll draw a little axis over here. Okay, and just bear with me for a second. This is west, this is north, this is east, and that's south, okay? So if I'm going 30 degrees south of west, that means my wind, my little red vector, is going to be 30 degrees like that, okay? Now, where do I put it? Well, we already know that it has to go tip to tip. Now, the magnitude of that is 70. So what I'm going to do is I'm going to put my vector here, tip to tip, like that, okay? Now, here's the challenging part. We need to know what this angle is. And we can figure it out because, look, we know that is 30 degrees. So now I'm going to do a little, let me zoom in. Now we know that this down here is also 30 degrees because of parallel line theorem. And therefore, my angle inside, which this whole angle, all of this has to add to 180 because it's a horizontal line. So therefore, my interior angle has to be 150. So that's 150 degrees. This vector, I'm going to erase this now, this little reasoning I did here. This vector here is 70 in length. That's the wind, right? The red one. So it's 30 degrees south of west. Okay, and now to complete the picture, I put my blue vector in. This is the one the pilot controls, that one, okay? But here's the deal this time. This time, we know what the airspeed is. The airspeed is 350. That goes with the blue one. So this one's 350, okay? And they're asking us for the heading. Well, the heading is theta, okay? So let's find theta, and to do it, this is not a right angle triangle, absolutely not. There's an obtuse angle in there. So I'm going to use sine law, sine of theta divided by 70. So remember how sine law works. The sine of the angle here divided by the opposite side equals the sine of 150 divided by 350. Okay, so let's go ahead and do the math. 70 times the 150 sine divided by 350 equals sine -1. I get 5.74 degrees. So my answer is theta equals 5.74 degrees. Now, if you look at theta, it is going north of the east line. So it's north of east. And that, my friends, is the answer to the question. That is your heading. So in other words, the pilot has to point slightly north of the east line in order to compensate for the southwest headwind, okay, or crosswind, or whatever you want to call it. Okay, that's it. So, ladies and gentlemen, what we're going to be doing tomorrow as well, or sorry, when you're listening to this now, so your homework for the weekend is this. Okay, now I have a worksheet that has 2 sides to the page. Okay, some of this stuff is about components and some of it is about relative motion. Okay, so read the question, give it a try, see if you can answer these questions. You'll have to think about some of them, but you've got to do some of the thinking. I don't want to just give you everything. So you do some of the thinking here. I'll tell you quite honestly that page 1 is all right angle triangles. So yes, there are like 11 questions, but they're easier ones. They're all right angle triangles, so that should make it a little quicker for you. Please notice that sometimes they try to trick you. Like if you look at question 10, they give you the water speed of the boat, 9 kilometers per hour, but then they try to trick you with the current, 2 meters per second. You need to make a decision there. You either convert to kilometers per hour or convert to meters per second, but you need the same units in the diagram, okay? So please don't be fooled by that question. Now, on the back of the page, there are 6 more questions, and these ones are sine and cosine law. Now, it says to use component. Don't use the component method. Okay? I just, honestly, the math for the wishes to fly questions, and a lot of these are wishes to fly. See how the pilot wishes to reach a city. The math for those, you won't like it. You're going to say, I should have just drawn the dumb triangle. Okay, so trust me, use sine and cosine law for these 6 questions. There are 2 of them that are particularly difficult to draw. Okay, but you know, we'll see. So challenge. So there you go. You like a challenge? Then that's great. Now 4 of them are pretty easy, and 2 of them are a little bit difficult. But I will leave it to you. Do the best you can. Okay, and we'll take these questions up on Monday. Now, answers are already posted, just the answers, so that you can see if you're doing it right. So the answers are posted underneath the assignment already. You're welcome. Okay. And otherwise, guys, enjoy your weekend. And please post your homework in OneNote. Okay. Someone asked me if they could redo one of the quizzes or whatever. If I don't see evidence that you're doing homework, so that this goes for anyone who wants to ask that question, I can't do that. It's just not right. To me, like, if you got to show me that the effort is there, then you deserve a second chance. Okay, so just keep that in mind, especially now that I'm starting to give back some of these tests, and maybe some of you aren't too pleased with it. So that's it. Have a good weekend, and yes, please do the homework and ask questions. We're going fast. You can't afford not to do the work. Okay. All right. Talk to you soon.